All right, hello everyone. Um, Today is November 19th, November 15th, 2023, getting towards the end of the year, and this is the libhal biweekly meeting. So for the agenda, we're going to talk about a couple of things that have been launched, at least in their alpha stage. We have libhal ICM, libhal XB, libhal Neo, libhal Nemia. We're going to do some special thanks about for the students who have worked on this, as well as we're going to go into some details about libhal 3.0 alpha 1. So first off, we have libhal ICM 001. It is a library for the ICM series of IMUs. It currently only supports the ICM 2948. It's a 9-DOF IMU with accelerometer, gyroscope, and magnetometer, meaning that you can measure acceleration, angular velocity, and also magnetic fields, either unidirectionally or, in most cases, use it to be a compass. Now, the 2094-8 IMU is one of the most common ICM chips you'll find out there. Adafruit, SparkFun, all of them will have this IMU available. There are a couple of quality checks that need to be done on the libraries before we can move them over to release version. So we're going to continue working on that, and we're going to continue making some decisions about certain things. I think we might even wait until magnetometer is supported in libhal, but I don't know. We might not wait for that. But yeah, so that pretty much goes for the rest of the libraries that you'll see here that are 001 in their version, is that they still need a little bit more quality checks before we make them full release. Oh, and note that if you do use any of these libraries that are 001 or at least the major number is 0, do know that any of your code that you use could break on you with any change of the version number. We may change API names, we may move code around. It is basically the Wild West until we move up to 1.00. We'll try not to be that aggressive with it, but you will have to deal with breakages. We also have XB001. This is a library to configure and communicate with XB wireless modules. Communication is performed over serial and acts like a transparent serial link between devices. If you never heard that term, transparent serial link, it's the idea that as far as your devices can figure things out, it just thinks that it's talking to some other device over serial. It doesn't actually realize the fact that the other device is being talked to over some wireless link. This is useful because you can just plug in separate devices using XB and not have to worry about a communication protocol on top of it. And depending on the version that you use, it could be anywhere between 600 feet to 40 miles. So very large range, although I think the 40-mile ones are pretty expensive. Now, libhal Neo is a library for talking to NEMA GPS, specifically NMEA, or I call them NEMA, or NEMIA. I'm not sure how you pronounce it, or if there's any way to kind of pronounce it without spelling out the letters. But it's meant for Neo series GPS modules. The GPS modules typically communicate over serial, and once configured, they periodically send their current location over serial. If you want to use it, you can use HAL Neo M9N driver, which is not featured on the right. This one is not one of those Neos. It's a different Neo chip, I believe. It's one of the 7 Ms, but we will probably add support later on. But the cool thing about the Neo devices is that they all follow NMEA. So there's a standard for how you communicate with marine electronic devices, typically sensors, and they all follow the NMEA standard. Now there's 2 of them. There's, I think, 3.0 and 2000. I think this one is 3.0. So I think NEMIA 2000 is the one that we're following. But this library is an interface library, software framework, and implementation for the most common NEMIA messages. Now, NEMIA is the standard for serial data network of marine electronic devices. And it contains a protocol for how GPSs and other marine and aerial sensors should communicate. Their structure is pretty simple. It's usually a money sign, a identifier, and then a sequence of values that are comma delimited. And then the last value at the end would be a new line character. It's all ASCII numeric characters, nothing too crazy there. And yeah, the cool thing about the NEMIA library is that it not only does it know how to scan for certain types of NEMIA messages, but you can also make your own, or more precisely, you can implement your own implementation of of a sentence reader. So every Nina message is basically a sentence, or is called a sentence. With this framework, you are able to take all your sentences, and if you know you have a single device that can spit out multiple of them, that you get the framework that allows you to take that serial data, map it, and route it to the appropriate sentence parser, have that parse it, and then you now have an updated value for your for whatever thing you're trying to sense, whether that be GPS information or heading or current velocity or other things. Now I want to give a special thanks to the Astraeus 1 senior project team. The people who are part of this who actually worked on these libraries would be Adrian, Mitchell, and Michael. Adrian and Mitchell were working on the ICM module. I forget who exactly worked on the XP. I believe it was just Adrian. Neo was mostly Adrian, and then Nina was Adrian's project specifically for the research project that I'm also managing as well at San Jose State. So this was the output of that research project, and the other three are from the Astraeus project. Now, Michael actually worked on the PCB that used the micromod system that we are trying to promote, so that's where his contribution comes in. All this stuff comes together with the board that he developed, and there are more libraries that we will be pushing out from this senior project, so I'm really excited about that, but that'll be later on. All right, now up for the big thing, the big update, which is libhal 3.0 alpha 1. So libhal 3.0 will remove boost leaf and replace it with C++ exceptions. Now I'm going to go over some of the pros and cons. The number one con for using exceptions is that error propagation now takes 21 to 27 times longer than if you just returned an error code. I will make a statement though, a little asterisk here, is that it's 21 to 27 times longer if you use a register with error code. If you use something bigger or a larger object, this gets smaller. Basically, the bigger your result type or your return object is to indicate error, or even if you just took it as an out parameter, you have to do all the copies. So all those copies as you go up and down the stack end up costing you. So when you actually try to do error propagation. So this is the best case for result types. It only gets worse if you make your error codes bigger. But this can actually even be brought down even smaller if you to around 7 to 14 times with optimizations. These optimizations that I've been working on in order to improve C++ exceptions for ARM devices on the ARM GNU toolchain. And luckily, these changes can be made without needing to, these optimizations can be introduced to your code without you needing to actually update your compiler or even recompile your compiler. A lot of the libraries, when it comes to exceptions, are simply linked in at compile time. So if you just change the definitions for different things, or just override like CXA throw and put your own implementation there, you can throw your exception however you like, which is what we're going to do. Pros, smaller binary sizes over error codes, result types, and all the like. Code clarity with C++ exceptions. I find it much easier to work with. I think a lot of the people feel the same. Another pro, better performance over result types. Still working on, well, I have the research for this, but anyone who's worked with result types compared to exceptions will know that on the happy path, you get better performance over having to do a check every single time. Another pro, this is huge, without boost leaf or really needing to do error propagation with error codes, there's no more need for macros. At least you don't have a need anymore. So the last macro pretty much dies. Yeah, which I'm pretty excited about. Now, another critical thing, is something I didn't bring up. This is actually something that's been in the back of my head for the longest time. I have been very concerned about this particular problem for the longest time, and I'm very happy I could just ditch worrying about it. So the removal of boost leaf also removes the boost leaf macros. There were two that were set in libhal, boost leaf embedded and boost leaf no threads. Boost leaf embedded and boost leaf no threads, well, if you tried to use multiple threads and you try to use boost leaf, the errors would collide with each other. So what you need to do is actually enable boost leaf for your particular thread mechanism. There is boost leaf for your RTOS, which you can enable, which works just fine. If you have a different RTOS, you need to then there's a couple of hooks that you need to use in order to support thread local storage for each one of your different threads to support locating where the errors get mapped to with exceptions. This is all to say that you would need to choose your libhal version and the binaries associated with that libhal version for every possible permutation of threading model that you might want to use. And I hated that idea. I hated the idea of having to have a LPC library or just a device library where you have it for Cortex M0, 1, 2, or sorry, 0, 0 plus, 1, 3, 4, 7, et cetera. But then also have another, that matrix grows for every single one of the threads that you want to support or operating system you want to support. And then you also have to include that for every single other MCU you want to support. Linux, or sorry, a host device, like host systems like Linux, Mac, or Windows, or whatever. But on top of this, even further, you have also like, RISC-V devices and all that. It can get really crazy. So I want to see if there's any way. I'm trying to make sure that we can keep as low of a number of binaries as possible, and Boost Leaf was actually getting in the way of that. So with exceptions, we now no longer have this issue. Now, I will continue to support libhal 2xy, basically 2.0, up until January 1st. It may take a little longer depending on how exceptions work, but I will at least be supporting up to that point. Even if beyond that point, you can still use the old code. The old code will still be there. All the binaries, like I did with 1.0 and 0.0, will all still be there. So you can continue to use old code and old projects. I still have, side note, JFrog still hasn't helped me out when it comes to the whole package repository thing. That's been a bit annoying, but I haven't had enough time to actually spend to kind of dig into them. I do have a meeting with the Conan folks tomorrow at 9. Just to kind of go over the ARM GNU toolchain, but also I'll probably bring up the fact that this hasn't been resolved yet. But yeah, regardless, I'm paying the money. Don't worry about it. The server will be there as long as JFrog is there, and you'll still be able to build your code at that point. Now, when you do build your projects using exceptions, do note that you will find a 8 kilobyte increase in binary size for the demos, for almost all of them. And then for SUC Robotics and Astrea's projects, it should increase by an amount less than 8K. Reason being is that there should be enough checks that when you remove all of them and port your code over, that you actually start getting some of the savings. It may even be better, but we shall see. It depends on if you got past the 300 something check barrier, which isn't super impossible. The ICM library, for example, has about 55 checks if you use all the APIs, which you may not. But if you did want to use everything in there, you end up paying the cost of 55 checks. I forgot to mute myself, so let's give me a sec as I mute my user. All right. Cool. Alrighty. So those are the big inspirations for why we're moving from Boost Leaf to C++ exceptions. Among the fact that I think that's just overall going to be a better experience for all of our users. It'll make our code easier. But I guess before I move on to the next item here, I did not think or believe that libhal could be performant code. I thought that all of our additional checks and all stuff like that we had to put everywhere in order to make sure that we could propagate errors everywhere would be such a dampener on our code that I couldn't, in good faith, say that our code could be performant. But with this move to C++ exceptions, this gives us a leg up above C and Rust. You cannot beat just not doing a thing. You cannot be more efficient than simply just not doing the thing that you didn't need to do. So with all other systems needing to actually check their results and us no longer having to do that, in the happy path, we are always performant. And that's going to be really nice. It also makes a lot of our code, we could trim off a lot of things out of our code. So yeah. And we'll make sure to design all of our code to be as performant as we possibly can. Yeah. So yeah, these are all the reasons why we're making the change. And this is what's happening with libhal 3.0. Now, a couple of the breaking changes are the obvious one, which is when we remove Boost Leaf, everything that had result T now just becomes T. So if something returned back an integer or result int, now it just returns back int. Everything that returns status now becomes just void. The other breaking change is that timeout objects now have the signature void void. They used to have bool void. They used to return back a bool. Yeah. Now what happens is that it throws stood error code timed out if it expired, otherwise returns normally otherwise. I want to dig into the timeout objects. So now you might be wondering, why didn't I keep it as bool? Why not, if you can just opt for that, why not just keep it as bool? We could just not have to worry about exceptions in this case. Well, why make timeout void and not bool? So let's look at the 2 bits of code here. Here we can see that we have returns bool, and if we do that, we have to then check. Let's say we have some while loop that does some work. We're going to check it. If it's not false, or we can say that the value of this thing should return back false if it timed out, or if it has not timed out, and true if it does time out. If it has timed out, we throw timed out. And if you're concerned about the not doing an inversion of the comparison that's inverted, most comparison operators, the compiler knows how to use the appropriate comparison operator, so it'll be one instruction no matter what. But let's say you did worry about that, well, we can invert that. But in this case, we return void. We just call a function, that's it. We know that the function will literally do nothing except check itself to see, hey, are we expired? And if nothing's happened, it just returns back up. So with bool, the driver gets the choice to either handle the timeout or throw the exception. We must now ask, do we want the driver developer to make that choice? How often will drivers handle timeouts compared to just propagating them? And does this lead to redundant code and cycles? So, do we want the driver developer making that choice? Well, we can give them that choice, but if they want to make this choice, all they need to do is catch the exception. If they want to handle this, they can just simply catch it. At 1 function deep on a Cortex M4 with optimizations, the optimizations that I provided, you lose an estimated 3,598 cycles. That is a lot, but with 12 megahertz CPU, that's about 300 microseconds. If that's too much for you, there actually are other solutions on how to time out things better than using this, but you'll need to actually take a steady clock and then work with that. Now, how often will drivers handle timeouts compared to just propagating them? So in my opinion, actually not in my opinion, the way I designed timeouts, they should be rare cases. You shouldn't really be using timeouts as control flow. They are how much time you have before you've gotten yourself into a bad position and you need to break out of procedure. The cases that I can think of in which we would want to break out of procedure are we are talking to a GPS and we expect a message back from the GPS no longer than, let's say, 100 milliseconds. We're on a single thread, or we're on a thread, and we're waiting that amount of time to get that response. We need that response to know what the next thing we need to do. If we have that timeout be, let's say, 110 or 150 milliseconds, and it exceeds that, we know that there's something wrong with the device. The device is not operating correctly. It's not within its spec. Something's very wrong. Another case, and this is something that has happened to the robotics team in the past, is we worked with a I2C device that did a thing called clock stretching. And the problem is that that device that did clock stretching would, well, the driver that we were using would lock up when clock stretching happens. It basically could not move forward unless that particular device let go. And that device also had a tendency to lock up. So you need to reset it. So this allows you to get out of that situation where you can say, hey, if the device hasn't come back to me in this amount of time, well, if you want to handle it, which is resetting the device, you can, and then you can try again. But you may want to actually reset the device, then return a different, throw a different exception, let the user then decide if that's something that they want to just handle or move forward with. Actually, in that case, I think handling it would be the best option because you know what to expect, and potentially, if you know what to return back to the user, that indicates that this thing locked up and that's expected, then that's fine. But in most cases, timeouts should be completely rare and not really occur very often. And does this lead to redundant code if we used return bool? Well, look at the checks we have here. Well, you may see it in this one spot and think this is fine, but we have to put this throughout all of our code, everywhere you see timeout. And we're going to be using timeout almost everywhere throughout the code base. I want most functions that have anything to do with time to be able to, or the ability to lock up, to have a timeout as one of its input parameters. So we will see this particular construct everywhere. Now what we've done is we could have just localized all of the checks and code inside the timeout function itself. We don't need to add another layer of checks on top of this. This thing already does a check internally. It has to check to see if it's expired. So we do a check on the inside. Why do a check on the outside? We could omit the check on the outside. We could just simply call the function normally and continue on as if everything's fine, and only deal with the error propagation or literally checking anything or doing any work once we have actually seen that, once we've actually observed we've expired, we now must start going through the exceptional path. And hopefully this will allow us to write way more branchless code. Way more code that doesn't really require as many branches. You just assume that everything works just fine. You just run through the code as much as you can and let the exception handlers and exception code handle the rest. And that's about it.